In this video, we will understand how data is represented and displayed in a computer. We have various types of data. For example, consider person. This person has different kinds of information. In this example, we have a name, which is of type string. We have a security ID, which can be a number. We have a height, which is a number. And we have a weight, which is also a number. What is a number system? A number system is a method for representing numbers and performing operations on them, which is basically divided into two parts: non-positional numbers and positional numbers. The idea behind a non-positional number system is that a set of symbols is used to represent numbers. However, these symbols have the same value regardless of positional they occupy in the number. In contrast, in a positional number system, the value of each symbol depends on the position it occupies in the number. Let's examine these two parts in details. One of the methods we use in non-positional system is the unary code. So what is the unary code? Unary code means that a set of symbols I use to construct numbers is equal to 1. That is, I have no numbers other than 1. And I build all numbers using only this one. As a result, if I want to represent the number 1, I draw one of these lines. If I want to represent the number 2, I draw 2 of these lines. If I want to represent the number 3, I draw 3 of these lines. And if I want to represent the number 10, I draw 10 of these lines. And now each of these lines that are drawn has a value of 1, regardless of where it is placed. Another example we can refer to is the Greek number system. In the Greek system, the set of our symbols is more than just 1. For example, I represents 1, V represents 5, X represents 10, and so on. If I want to represent the number 1, I use 1. If I want to represent the number 2, I use 2. If I want to represent the number 3, I use 3. If I want to represent the number 4, I can use either 4 or 4. For 5, I use V, and similarly for 10, I use X. But what about the positional number systems? In a positional number systems, the value of each digit depends on its position in the number. The set of numbers in a base R that you can choose from to construct a number in a base R is equal to from 0 to R minus 1. For example, the set of digits for a number in base 10 is from 0 to 9. Okay, for example, let's consider the number 123. The value of digit 3 in a 123 is 3 times 1. The value of digit 2 is 2 times 10. And the value of the digit 1 is 1 times 100. But to make the concept clear, let's take another example. Using the same digits, we can form another number. For example, 231 or 231. You can see that when the digits are rearranged, the value of the number also changes. The value of the 1 is 1 times 1. The value of the 3 is 3 times 10. And the value of the 2 is 2 times 100. As a result, the value of each digit is related to its position in the number. The point is that the further a digit moves from right to left, the greater its value becomes. For example, if we consider this number, you can see the position of digits, and below that, you can observe the value of each position. Since the base of our number system is 10, we take the base as 10. Therefore, as we move from right to left, the value of each digit is multiplied by the base, which is 10, and increases. In a binary system, the base is equal to 2, and the set of digits is 0 and 1. These digits, 0 and 1,
are important because the foundation of how computers works is based on the binary numbers. If we want to go one level lower, for example, consider a wire with an electric current flowing through it. If the current is low, it means 0, and if the current is high, it means 1. Each digit in this system is called bit, which can be either 0 or 1. Now, we can place several of these bits together to represent more state. For example, placing 4 bits together create a nibble, which practically covers 16 different states. Also, placing 8 bits together produce a byte, which covers 256 different states. The byte is a more important unit in the binary number system. Now, let's examine the different state of a nibble so that the concept becomes clear for us. As we mentioned before, we have a 4-bit nibble. At the top, you can see the positions of the digits, and at the bottom, you can see the value of each digit. Because in the binary number system, the base is 2, as we move from right to left, the value of each digit is multiplied by 2, such that 2 to the power of 0 equals 1, 2 to the power of 1 equals 2, 2 to the power of 2 equals 4, and 2 to the power of 3 equals 8. Now, let's start counting in the nibble. Let's start beginning with 0.
For number 0, we have no 1, no 2, no 4, and no 8. What about number 1? In the number 1, we have 1 1, no 2, no 4, and no 8. For the number 2, we have no 1, 1 2, no 4, and no 8. For the number 3, we have 1 1, 1 2, 0 4, and 0 8. And for the number 4, we have 0 1, 0 2, 1 4, 0 8. And for the number 5, we have 1 1, 0 2, 1 4, and 0 8. What about number 6? In the number 6, we have 0 1, 1 2, 1 4, and 0 8. And for the number 7, we have 1 1, 1 2, 1 4, and 0 8. For number 8, we have 0 1, 0 2, 0 4, and 1 8. Number 9. In the number 9, we have 1 1, 0 2, 0 4, and 1 8. And number 10, we have 0 1, 1 2, 0 4, and 1 8. What about the 11? In 11, we have 1 1, 1 2, 0 4, and 1 8. 12. In the 12, we have no 1, no 2, 1 4, and 1 8. 13. In the 13, we have 1 1, 0 2, 1 4, and 1 8. Number 14. In the 14, we have 0 1, 1 2, 1 4, and 1 8. Number 15. In the number 15, we have 1 1, 1 2, 1 4, and also 1 8. I hope the topics has become clear to you. The octal number system. In octal system, the base is 8. The set of digits that can be chosen for each position ranges from 0 to 7. Now, if you consider a 4-digit octal number, you can see the digit position at the top and the positional values at the bottom. And since the base is 8, as we move from right to left, the value of each position is multiplied by 8. 8 to the power of 0 equals 1. 8 to the power of 1 equals 8. 8 to the power of 2 equals 64. 8 to the power of 3 equals 512. Now let's start counting. We want to count from 0 to 10. Now, as you know, since each digit in these systems can be chosen from the range 0 to 7, counting up to the number 7 is easy. Let's start with 0. For the number 0, we have 0 ones. For the number 1, we have 1 ones. For the number 2, we have 2 ones. For the number 3, we have 3 ones. And in the same way up to 7, for the number 7, we have 7 ones. But for the number 8, we have one group of 8 and 0 ones. For the number 9, we have one group of 8 and 1 ones. For the number 10, we have one group of 8 and 2 ones. This was a short overview on the octal number system. Okay, what about the hexadecimal number system? In this number system, the base is 16 and the set of allowed digits for each position ranges from 0 to 15. However, there is an important point to consider. The set of digits is as follows: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And to represent the numbers 10 to 15, since we cannot use two symbols to represent a single digit, we must replace them with a single symbol. As a result, each number from 10 to 15 has a unique symbol. 10 goes to A, 11 goes to B, 12 goes to C, 13 goes to D, 14 goes to E, 15 goes to F. These symbols are used accordingly. Now consider the 4-digit number. At the top you can see the positions, and at the bottoms the positional values. Because the base is 16, as we move from right to left, the value of each position is multiplied by 16. Now, let us start counting. As you know, in base 16, for the number 0 to 9, the value of each number is simply the digit itself multiplied by its positional value. Therefore, counting is very easy for us. But for the number 10 is equals to A, 11 is equals to B, 12 is equals to C, 13 is equals to D, 14 is equals to E, 15 is equals to F, 16 is equals to 10. Which means we have 1 16 and 0 ones. 17 is equals to 11. Which means we have 1 16 and 1 ones. And up to 31, which is equals to 1F, meaning we have 1 16 and 15 ones. And 32 is equals to 20, meaning we have 2 16 and 0 ones. Okay, up to this point, we have shown the representation of numbers in base 10 to 8 and 16. Before continuing, please subscribe the channel and like the video. And if you have any question, you can ask them in the comments and I will answer. Now that we understand how we can represent number from base R to base 10, we want to see how we can convert a number from one base to another. For example, converting the representation of a number in a base R to the representation of the same number in a base P. To do this, since working with the base 10 is easier for us, we consider base 10 as an intermediate base and perform the conversion through base 10. Of course, sometimes we can convert base directly to each other, which we will discuss later. To convert from base R to base 10, we need to use operation of summation and multiplications. And when we want to convert from base 10 to base P, we use division operation. For example, we want to convert the number 86 from base 10 to base 2. To do this, we use successive division by 2. As you can see, 86 divided by 2 equals 43, with a remainder of 0. 43 divided by 2 equals 21, with a remainder of 1. 21 divided by 2 equals 10, with a remainder of 1. 10 divided by 2 equals 5 with a remainder of 0. 5 divided by 2 equals 2 with a remainder of 1. 2 divided by 2 equals 1 with a remainder of 0. And 1 divided by 2 equals 0 with a remainder of 1. As you can see, we continue the division until the quotient becomes 0. Now, if we write the remainder in reverse order, the representation of 86 in the base 2 is obtained. This digit is called the least significant bit, and that digit is called the most significant bit. Now, let's take an example of converting from base 10 to base 8. Consider the number 86. 86 divided by 8 equals 10 with a remainder of 6. 10 divided by 8 equals 1 with a remainder of 2. 1 divided by 8 equals 0 with a remainder of 1. And this gives the representation of the number 86 in base 8. And if we want to convert the same number to base 16, 86 divided by 16 equals 5 with a remainder of 6. 5 divided by 16 equals 0 with a remainder of 5. And this gives the representation of number 86 in base 16. Now, the point to note is that the number 86 has a 7-digit in base 2, 3-digit in base 8, 2-digit in base 10, and 2-digit in base 16 as well. As a result, the larger the base, the greater the positional value. And the greater the positional value, the fewer digits are needed. We can use this rule to shorten the length of a number. For example, if you have a URL, you can reduce its length by increase the base. In this video, we talked in detail about converting from base R to 10. But here, we provide more complete supplementary explanations. If I have a number in base R and want to convert it to base 10, I proceed as follows. As you can see, above is the position and below is the value of each position. And if we consider the digits as A, we have A0, A1, A2, A3, A4. If we want to convert the number from base 2 to base 10, the result is the sum of the AI times R to I power, where I goes from 0 to, for example, 4. Suppose the base R equals 2. We have a representation of number 101101110 in base 2, and I need to sum of these values together. That is 128 plus 32 plus 16 plus 4 plus 2, which result in 182. The representation of the number in base 10. Suppose R equals 16 and we have a number A4E whose positional values are 1, 16 and 256. As I mentioned, the sum is I times R power to the I gives the result in base 10. That is 10 times 256 plus 4 times 16s plus 14s equals to 2638 in base 10.
Now, sometimes we can convert between base directly, especially when one base is a power of another base. For example, if we want to convert from base 2 to base 16, the set of digits in base 16 is 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. We say that these 16 different cases correspond to 4-bit representations in base 2. Now, if you want to convert the base 2 to base 16, it is enough to separate the bits into groups of 4 and write their corresponding values in the base 16. Let's look at an example together. Suppose we want to convert the number 1011001011001100 from base 2 to base 16. Here, we separate the first 4 bits which correspond to C in base 16. The next 4 bits correspond to 6 in base 16. The next 4 bits correspond to 1 in base 16, and the last 4 bits correspond to B in base 16. Likewise, we can easily go into opposite direction by converting each digit of a base 16 number into its corresponding 4-bit representation in base 2. Naturally, we can use this method to convert from base 2 to base 8 or vice versa, because 8 is 2 to the power of 3. To convert from base 2 to base 8, we need to separate the bits into groups of 3 or do the reverse. So if I have a representation in base 2, for example 100, 110, 101, 111, converting this number to base 8 is done by separating the bits into groups of 3, and converting them to base 8 is the first 3 bits become 7, the next 3 bits becomes 5, the next 3 bits becomes 6, and the last 3 bits becomes 4. And the correspondences can be represented in this way and likewise in reverse. Binary encoding and binary decoding. As we know, the computers we currently use operate based on base 2. Therefore, all the data we have, which we usually want to input into a computer and which is generally in base 10, must be converted to base 2. This process is called binary encoding. Now, the computer performs operation on this data and gives us an output. Since the output is essentially in base 2, it must be converted to base 10. This process is called binary decoding.